Okay, so we're starting with the function f of xy equals 5x squared minus 3x plus 5y plus 3y squared plus 7xy. And we're looking for the critical points, and then we want to determine if it's a max, min, or a saddle point. So to start, we're going to take the partial derivative with respect to x. It's going to give us 10x minus 3. The 5y will be 0, the 3y squared will be 0, 7xy, I treat the y as a constant, so that's like the 7 and the y are the constants, times x, to be plus 7y. And the partial derivative with respect to y, derivative of 5x squared will be 0, negative 3x will be 0, 5y will be 5 plus 6y, and again here the 7x, x is a constant, times y, so we get plus 7x. Then I'm going to go ahead and take my second partials. It's just easier here for me. So I'm going to start them off with fxx and then fxy. So both derivatives of this, first with respect to x, then with respect to y. It's just an organizational thing so that when I go to find d later, it's easy. Derivative of this with respect to x is just 10. Everything else gives 0. Derivative of that with respect to y is just 7. Everything else is 0. Fyx and Fyy, I set up the space for them first here. Derivative of this with respect to x is 7. And derivative of it with respect to y is 6. And then I'll just very quickly note that these two across from each other should be equal, and they are. So that provides a checking mechanism for my first and second derivatives, really. If I make a mistake somewhere, those two things probably aren't equal. If I didn't make a mistake, they're likely that they are equal. So if you're taking a quiz or something and they're not, I mean, you have to make sure you're in the right, you have the right ordering of these functions, otherwise it can be problematic. Okay, so we found our first order partial derivatives and our second order partial derivatives. Now we want to find our critical points, which is setting these two functions up on top to 0. So we're going to get 10x minus 3 plus 7y equals 0, and 5 plus 6y plus 7x equals 0. And both of the x's and y's in both equations are to the first power. So this is a linear system of equations. Because of the coefficients, I can't divide anything easily and avoid fractions. I'm going to solve this system using elimination. So I'm going to rewrite it, leaving the x's and y's in standard position, 10x plus 7y, and moving the constants to the other side. 10x plus 7y equals negative 3, and this one will be 7x plus, I'm sorry, that equals positive 3. This one will be 7x plus 6y equals negative 5. I'm going to solve for the x's first. So I'm going to multiply the top equation by 7 and the bottom equation by negative 10 times 7. This equation by negative 10 so that I can make these coefficients of x opposite. So I'll get 70x plus 49y equals 21. And negative 70x, that's why one's positive and one's negative, so I can add them and get 0. Minus 60y equals positive 50. I'm adding these up to eliminate these x's. I'm going to get negative 11y equals 71. And then divide by negative 11 to get a y is equal to negative 71 over 11. I want to leave that as a fraction, but I don't want to try to plug that back in and solve for x unless, if this were 11 times that, sure, no problem. But it's not. So what I might do instead is just take my original two equations here and now try to eliminate the y variables. So to do that, I would multiply the top equation by 6. Oh my gosh, my cat just joined me. Not making it any easier. Okay. Oh, sorry. Sorry about that. Sorry, buddy. Totally dropped her. Okay. What am I doing? Top equation multiplied by 6. So 60x timesing this guy by 6. 60x plus 42y equals 18. And the bottom equation, I want to multiply by -7. Is that right? You're trying to eliminate the y. So yeah, -7. So negative, something feels wrong. 70x, oh, sorry, not 70. 7 times 7 is 49. Negative 49x minus 42y, that's going to cancel those y's out when I add them, equals positive 35. Add them up. Negative 11x, these cancel, equals 53. So x is negative 53 over 11. And, that's the part I think that most of us will not have done for a while, is solving a system of linear equations using elimination. So I didn't do this in class because we had a nonlinear system. So there's a linear system giving us kind of icky rational results, but not a big deal. Our critical point is at negative 53 over 11, negative 71 over 11. I feel like it should be positive 53. Yeah. Yeah, this is positive 11. Sorry. And this is positive 53 over 11. So, okay. So lots of room to make mistakes. You see, I just made two, one there and another one here. But that's my critical point. And then we want to go back and discover what, whether this forms a local min, a local max, or a saddle point for our original function. Also, we're not going to have to plug these numbers into the original function. So we're just going to determine if it is a minimum, if it has a minimum or a maximum or a saddle point at that place. We don't have to plug those numbers back in. So scrolling back up to our constants here, our second derivatives, they're constants, 10, 7, 7, and 6. So again, I don't have to plug these numbers in because these second derivatives don't depend on x and y, but I do need to find this determinant. So d is equal to the determinant of those coefficients, 10, 7, 7, 6. 10, 7, 7, 6. Take the determinant of that. It's 10 times 6 is 60. The down product minus the up product minus 49 is 11. Greater than 0. So I either have a maximum or a minimum. And then we want to look at the second derivative with respect to x, which is, really at this point. But again, these are constants. So it's this 10, which again is greater than 0. And I think in my mind of, oh, that's concave up. So that means I have a local min at that critical point. Positive 53 over 11, negative 71 over 11. Okay, that's it. Let's see.